Alright, so this is Electron Configurations. This is proficiency number 1. So instead of orbits, we have orbitals. And what they are is it's a mathematical function, really. But basically it's a way to represent where electrons probably spend 90% of their time. So it's kind of vague, right? This probably and this 90% is kind of, you know. There's 4 different types, really, that we're going to talk about. Really, we're only going to talk about 3 a lot. S, P, D, and F. Well, we're kind of going to ignore F a lot. All right, so here's an S orbital. It's not a circle like Bohr's. It's a sphere, right? 3-dimensional. As you can see, there's a higher probability of electrons near the middle, which makes sense if you think about the charges of an electron and the charge of a nucleus. And then as you get further out, there's less likelihood of finding an electron. It's all about probabilities. Likelihood of finding electrons. Probably we'll find an electron. So S orbitals hold 2 electrons. P orbitals, again, all orbitals can hold 2 electrons. There's just different types of each. So, for instance, there's 1 type of S, so it holds 1 electron. Well, there's 3 types of P's, so since there's 3 types, each type can hold 2. P's can hold a grand total of 6 electrons. And so you see, it's pretty easy. They're little dumbbell shapes. PX, PY, PZ. So PX goes along the x-axis, PY goes along the y-axis, and PZ goes along the z-axis. And each of those can hold 2 electrons for a grand total of 6. And again, this just shows you kind of where the greatest concentration of electrons is at. D, way too fancy, right? We don't need to worry about D, X, Y, D, Z, X, D, Y, Z, D, X squared minus Z, right? You don't need to know all that stuff. But there's 5 different types, and they're located in the transition, right? There's DYZ, DXZ, DXY, DX squared minus Y squared, and DZ squared, yeah. So don't worry about it. Know that there are 5, know that they hold 10, but you don't need to know their names or any of that kind of stuff. All right, and here's where they were located. Right, the periodic table, if you were to look at it, you can tell it's divided into sections. You can tell that there's this 2-column-wide section, that there's this 6-column-wide section, this 10-column-wide section, and this 14-column-wide section. That's not a coincidence. Okay, the S's all hold 2, so these are the 2s. The P's all hold 6. The D's all hold 10, and the F's all hold 14. So it's not coincidence that it's like that. It makes sense. Okay. So naming. Here's really where the proficiency starts. Here's where what you have to do. Basically, what you're doing is you are telling how many electrons are in a given element and where they appear. So, for instance, oxygen. Let's go back and look at this. Oxygen is located right here. So, 1s, and I don't know why this is green. It should be purple. Okay? 1s, 2. Because there's 2 electrons. I know what you're doing. I'm trying to help you.
Oh, thank you.
So 1s, 2. Then you got 2s, 2. Then you go into the 2p and you go over 1, 2, 3, 4. So when you look at the oxygen, it's 1s2, 2s2, 2p4. I know this is kind of difficult. The best way is just to look at a lot of examples until your brain kind of sees the pattern. Okay. This is for us. For this class, you must fill one orbital before moving on to the next. You can't have unfilled orbitals, when in reality, yes, you can. But for us, just makes it easier, you can't. All right, so how many electrons should sodium have? If you look at a periodic table, and you guys don't have remotes, and I didn't want to mess with them, but if you look at a periodic table, sodium has an atomic number of 11. So if it has an atomic number of 11, that means it has 11 protons. So how many electrons does it have? 11. Okay. What is the correct electron configuration for potassium? Again, this is probably hard to do without a periodic table in front of you. But if we were to go back, potassium is here, I believe. So, if potassium is right here, you're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, because it's in the first of the s. Okay? So all you're doing, you're just listing off all the electrons that are in it. I know it's kind of confusing. All right, now what about phosphorus? Same thing. This is phosphorus right here, I believe.
Yeah.
So, right there, yeah. So, again, 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3. Okay. There are shortcuts. Because as you can imagine, when you start naming those long elements, you got huge, long, enormous names, and it's just a pain in the butt. So, what we can think about is the whole reason we care about electrons, okay, a lot of the reason we care about electrons is because we care about bonding. We care about chemical reactions and bonding and how the elements are going to interact with each other. The only ones that really matter are the valence electrons, the ones on the outside. We don't care about this stuff in the middle. Once something's been locked away in the middle, I say the middle, I mean inside of an inner orbital, they don't really do a whole lot, and we don't really care a whole lot about them. So, if you were to look at francium, bottom left corner, number 87, all right, that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, right? Forever, and it's going to take forever to get through there. Well, really, we don't care about all those electrons because they're locked away in the middle. They don't do any reactions. So all we care about is the one on the outside. Francium only happens to have one on the outside. What we can say is it has the same electrons as radon plus the 7s1 electron. And the way to write that is brackets radon 7s1. Because if we go back to that slide we've looked at 1,000 times, here's francium. Okay. Every time your electron fills up and gets to this line, all those electrons get locked away and they move and they open up a new shell outside of it and they start over. And then again, they fill it up, it gets locked away, and they start a new shell on the outside of it. So the stuff inside doesn't matter. So francium filled its shell up, locked it away, and opened up a new one. So all we care about is how many it has since it's locked up its last shell, which in this case is only one. So instead of writing out all that stuff, which would have to include F's, no fun, we can just say, has the same stuff as radon, plus 7s1. And it makes our lives so much easier. Important thing, you can only put in brackets these guys. Okay? The helium, neon, argon, krypton, xenon, and radon. Those are the only ones you can put in there. You can't, so for instance, you want to talk about oxygen, you can't say, oh, it has the same as carbon plus 2. No, you can't do that. It's got to be those ones on the far right corner. Okay. That's the first half of Proficiency 1. The second half, remember, is the arrows. So, this guy, his name was Pauli. He came up with an exclusion principle. So we named it Pauli exclusion principle. Basically, what he said is, in a given orbital, no two electrons can have the same spin. Don't really worry about spin at this point. Just know that two electrons have to have opposite spins, and you signify spin by either an up arrow or a down arrow. It's easy with the S because there's only one orbital, so one gets an up and one gets a down. The problem is when you get to P's and D's, where you have 3 orbitals or 5 orbitals, there's multiple ways to do that. So what you have to do is you have to put 1 electron in each orbital before you can double them up. And think of it like this. Electrons are negatively charged. So if there's extra space, an electron is going to want to keep its space from another electron because they have the same charge, so they're going to repel each other. So it's going to want to keep its opposite its space as long as it can. All right. So helium is easy. It has 2 electrons. It's 1s2. So your 1s box has 2 arrows. 1 up, 1 down. Ah, bummer. All right, this will be the last thing we do today. Whereas these are a little different. So fluorine, for instance. What is fluorine's electron configuration? What was that you said? 1s2, 2s2, 2p5. Okay? So how you would write that, how I would write that, is 1s, and instead of boxes, I just do lines. It's only a quarter of the work, and it works as well. 1s, 2s, and then 2p is going to get 3 lines, because there's px, py, and pz. So again, up, down, we filled up our 1s and our 2s. Now when it gets here, you have to put 1 in each box before you can start doubling them up. Okay. Silicon. 1s, 2s, 2p, 3s, 3p. Again, fill them up, down, up, down. Now, even though you know you're going to fill this one completely up, it's just a good habit to get into to put them all up first and then start going down. It's just a good habit. And then up, and then down. And now, how many lines am I going to get in that box for silicon? 2. So, remember, that's how it needs to be. If you were to do this, you're wrong. Because 2 electrons with the same charge aren't going to want to be next to each other. They're going to repel each other. Unless they absolutely have to be. So that would be the correct for that. And then last but not least, chromium. My goodness, I'm cutting my work out for me, aren't I? 1s. That's kind of going to be a little close. There we go. 1s, 2s, 2p, 3s, 3p, 4s, 3D. And then, of course, you get 5 lines. So, I'm not going to waste the time, but, right, you would fill these all up. Right, these would all be filled up. Jeez. Now, chromium. Wow. All right. Now, chromium is 4 in. So, same thing. You have to put 1 in every box before you can double them up. And since you have 5 boxes, you're never going to double them up, and that's what it looks like.